Yes, as Marcus said, I'm Sergio. This is joint work with Jonathan, who was my senior at the time, and Alejandro at Chalmers. So there we go. So the primary question we're trying to answer here is, we're dealing with smart contracts, we're dealing with the blockchain, and we're trying to answer the question, what are the necessary properties for correct smart contracts? If you're going to write a smart contract that is correct, if you take all the smart contracts that are correct, what properties do they have in common? What properties must they have? And perhaps equally as importantly, how do we enforce these properties? And sort of the spoiler here is that the properties that we've identified, we call them safety properties, which are liveness and linearity, and I'll define these a bit later. And our idea on how to enforce these properties is by block checking a type chain, effectively reformulating the blockchain into what we call a type chain, and then block checking, which is what miners would do. And now the point of the talk is to sort of go through these properties and then identify one solution we think is a solution, which is to block check a type chain. One interesting thing to note here is that we believe that if you're going to get these properties, safety properties, then you're effectively going to have a solution that looks like block checking a type chain. So it seems that if we're ever going to have these properties be universally enforced, then it's going to look something like a type chain. Now, this is a short paper. This is much more of an idea and a work in progress than it is a complete solution. It is something that we're working on. We have solutions to all of the sort of properties that I'm going to, or rather mechanisms to implement all of the properties that I'm going to talk about, but this is still a work in progress. So I'm more than happy to take any questions at the end and sort of more interestingly have a discussion on these ideas. So the rest of the talk is going to proceed as follows. I want to talk a bit about blockchains first, just in general, just make sure we're on the same page about what a blockchain is and general structure of it, and then how buggy contracts generally have their bugs arise, or rather many bugs in contracts seem to arise from language design. So we should look to redesign language that we use to write smart contracts if we're going to deal with bugs in smart contracts. Then I want to really define those universal safety properties that we were just talking about. These are the properties that are necessary for contract correctness, properties that must hold for any contract to be correct. And sort of the key point of this part is to discuss how a language-only approach is insufficient because of inter-contract interactions, because contracts can interact with each other. Purely handling this at the language level is insufficient. We actually need to redesign the blockchain. And then finally, talk about type chains, which is our type-driven, language-aware redesign of the blockchain. The key property of type chains is this notion of block checking, which is what actually statically enforces the safety properties. And perhaps equally importantly, type chains are extensible. Obviously, safety properties are not all of the properties that would fix all the bugs. And so it's important that type chains are extensible to admit nearly arbitrary functional correctness properties. And we'll discuss one technique for doing so. So this is sort of the outline of the talk. Let's start with the blockchains portion. So I'm going to divide blockchain into these three massive components. There are transactions. Transactions are things that operate on smart contracts. They modify the state of a smart contract, which in general means transferring assets or changing bookkeeping of smart contracts. Smart contracts themselves are arbitrarily stateful programs that compute on these assets. And an asset can be money, it can be a tangible item, say the title to a car, or the title to a house, or some kind of sub-asset, tokens as they're called in things like Ethereum. And then the third component that I want to identify here are miners, which are machines, all of them decentralized, that are responsible for deploying contracts, running the transactions, and more importantly, reaching Byzantine fault-tolerant consensus on the ordering of smart contracts and transactions and the result of executing transactions and deploying smart contracts. And sort of a different way to look at this is to look at the blockchain in this manner, where you have contracts, these little documents here, And then you have transactions, and the miners down here at the bottom of the slide are imposing an order on the blockchain. And the smart contracts have state, and every time a transaction runs, it can modify the state of any existing contract. And so these miners are recording a state, rather an order, or agreeing on an order, executing these contracts, and then recording the modifications to the state of contracts, to contract state. The contracts look sort of like this. Here's the running example, my favorite running example, which is an auction contract. I just want to walk through this contract rather quickly here. So the contract on the left and transaction on the right. So this contract on the left is an auction contract. So you take bids, and then the hope is that the maximum, or rather the maximum bid, wins the auction. So if we sort of run through this, it's kind of like Rust, but you can just imagine it's ML or C++, or choose your favorite language here. So the idea behind this contract, we just go from the top to bottom here. You have this named contract called auction, and this is the piece of the auction that would be valid to run when the auction is in some open state. It has one method that you can call that takes in money, and then the logic is in that middle block there. And it says if the auction should close, so this is a timed auction, then close the auction. Otherwise, if the amount is less than or equal to the maximum bid, then return that amount to the sender because they're not the winner. Otherwise, or rather they're not the current leader. Otherwise, set them as the current leader. On the right here is some idea of how you might actually invoke this contract with transactions that are themselves programs. Smart contracts are programs, and so are transactions. You can call the bid method, and presumably this contract has other methods. This one's called do something, and do something might call bid, and might do random things. It might call other contracts. Who knows? So what's wrong with this contract? This contract is quite buggy. There are a few things wrong with this contract. So first is that if you look at these two branches here, in the case that it should close, or in the case that that should be, in the case that it should close, or the case that that the winner is set to the new amount, we actually lose money irreversibly. In the first case, we should return the amount to whoever bid. Here we just close the auction, but that first branch should return the amount to whoever bid. Otherwise, that amount is just lost forever. In that second highlighted branch there, we should actually return the previous bid to whoever was the leader at the time. So in both of these branches, value is just lost irrevocably. And what's happening here is that in the real world, if I give you $1, I lose the $1, but the dollar still exists in the real world. The total sum of all assets, unless you burn money and commit a federal crime, is always preserved. And ideally, we want the same property in our smart contracts. It's a necessary property for assets in general. And smart contract programming languages at the moment don't enforce this property at all. So it's very easy to lose money, or equivalently to just create money from nothing. Another barrier is that this contract doesn't consider that transfers are fallible. If you look at how transfers are implemented in, say, Ethereum, transfers can fail due to, in particular, resource limit exhaustion. If you exceed your stack limit, if you run out of gas, which is a compute resource, this call can fail. And so it's up to the caller to check whether this failed. If you don't check whether this failed and it did fail, well, you run into a similar issue as before, where you lose money. In this case, you don't return the amount to the sender. Yet another bug here is that methods themselves can throw exceptions. Just like a transfer can fail, in that case, by returning a true or false, methods can also fail by throwing exceptions, again, in blockchains like Ethereum. And so you need to check those exceptions if you really want to ensure that what you think is going to happen will happen. One particularly important issue with not checking exceptions is that depending on how the exception occurred, you might have a partial rollback. And so you might end up in a state that you don't expect, or you might have a full rollback where at least you know that you're where you started. But in the case of a full rollback, you made no progress. And it's possible that your contract gets in a state where only exceptions can occur. And if only exceptions can occur and it results in a full rollback, then the contract can never make progress and funds are just locked forever. Finally, one last note here is that this state checking, here I've sort of written in a way that might make you think this is statically checked, but languages like Ethereum, this state check is actually a dynamic check. Again, that will throw an exception if this is not in fact the state that the contract is in. Just like before, this exception can result in locked contracts, partially rolled back state, resulting in inconsistent state, resulting in incorrect logic, and so on and so forth. So all of these issues are caused by language features. If we had a language that had linear assets, well, we couldn't have nonlinear assets. If our language didn't have exceptions, well, then we wouldn't have the exception issues, and so on and so forth. And so it seems like we should definitely improve the language. These features that have been included or features that are missing from languages are a big part of the reason why these bugs are occurring. And to sort of exemplify this point, these kind of bugs have led to the loss of hundreds of millions of dollars. One famous instance was the DAO attack, which was hundreds of millions of dollars that were just stuck in the contract, or rather stolen from the contract. And to resolve this issue, Ethereum decided to fork into two, which is very odd given that the blockchain should be immutable, in order to effectively try to return the money back to whoever the money was stolen from. And so these bugs really lead to loss of hundreds of millions of dollars in the real world. Sometimes it's so bad that you have to fork the entire blockchain. Most of the time, you're just out of luck. So ideally, it really seems like languages are part of the problem. So let's sort of improve the language to improve our contract correctness. So that's all I want to say about blockchains. Now I want to get into these actual safety properties. We identified sort of mechanisms and languages that are failing us, but what are the overarching properties that we want out of these out of these smart contracts that cover these properties? So here's what's wrong. What are these safety properties? Well, the first one is clearly linearity. We want to deal with, we don't want nonlinear assets, so let's have linearity. We should have it be the case that assets are never lost, I should say nor duplicated. If you have an asset, it can move, but it can never be lost, it can never be duplicated. Simple enough. Perhaps slightly more complicated is realizability, is what I'm calling realizability. And that's the idea that a contract can always be run to successful completion. And now this obviates the ability to have exceptions. This obviates the ability to have resource exhaustion be a component of a blockchain. It actually obviates the entire need for something like dynamically checked gas. So this is clearly a very difficult property to get, but it seems clear that if we're going to have correct smart contracts, then they're going to be realizable. And more importantly, all correct smart contracts must be realizable. There is no correct smart contract that can get into a state that is not realizable. That is always a contract that can lock funds. And then sort of related to realizability is the liveness of assets. What we want is that if a contract has assets, then it should never be able to lock those assets. It should always be possible to move those assets around. There are caveats here in sort of our definition of liveness, but the general idea is that it should always be possible to invoke the contract in such a way that assets are moved, irrespective of the state of the contract. Now, a key point here is that in order for these properties to mean something, they have to be statically enforced and they have to be state independent. Certainly, if they're state dependent, then you can get into a state where these properties don't hold and you go back to the same issues. But more interestingly, if these properties are maintained at runtime, then you can't possibly have realizability. If at runtime you identify, oh, this asset isn't being treated linearly, then what do? If you fail, then you lose if you fail the contract, then you lose realizability. And if you allow it to continue, then you don't have linearity. And so in order to get these properties to actually mean something, they have to be statically enforced and they have to be state independent. Interesting relationships between these properties. If a contract has assets and it has liveness, then it must be realizable. But there's no relationship between linearity and realizability. You can have a contract that, if a contract always terminates without moving assets, then the assets are in fact treated linearly. But it's also possible that that a contract is linear in the states that it can execute, And if it doesn't execute, then obviously it's linear by default. So there's no relationship there. Going back to our running example of the auction to see how it would affect this contract. If we have linearity, then in these branches, we would need to do something with the asset that hasn't been moved. In that first branch, we need to do something with amount. In that third branch, we need to do something with max bid before it's overwritten. So linearity would resolve, or rather would preclude the bugs in those two branches. So amount must be used exactly once. Realizability would mean that you wouldn't have to worry about these two calls here somehow aborting the contract or leaving the contract in some broken state. So these calls either can't fail, or the language would somehow enforce that they are checked. And finally, liveness would allow you to say that if the contract is open, then you can definitely move money around, which is a nice property to know. So again, improve the language, you improve contract correctness. Now, it'd be quite nice if this was kind of the end of the story. Let's just have a really nice language. There are languages that have some of these properties. As far as I know, there's no language research otherwise that has all of these properties. But unfortunately, improving the language is not sufficient. And the reason for that is because contracts can communicate with each other. So if you have a contract A that's written in your very nice language with these properties, and a contract B that is written in language without these properties, then the first contract can't say anything about the properties. It can't soundly say anything about the properties. As an example, consider linearity. You have a contract A that talks to contract B, where A treats assets linearly, but B does not. Then B is free to duplicate and lose A's assets without A ever realizing it. And so if you really want to solve this problem, or rather to actually solve this problem in a sound manner, then you need a language-aware redesign of the blockchain. The blockchain itself needs to enforce these properties. So one caveat here is rather an unfortunate caveat, that you can't possibly get these properties from existing blockchains like Ethereum, because they don't enforce these properties at the blockchain level. And because you need them to enforce these properties at the blockchain level, we need a new blockchain. We need a redesign of the blockchain. So those are the safety properties. And then our redesign of the blockchain, we call a type chain. A type chain is much like a blockchain, except you add the words typecheck, type, and blockcheck to the definitions of the components of the blockchain. So transactions are type programs, miners blockcheck, and blockchecking is effectively type checking in a Byzantine fault-tolerant way, these transactions, and smart contracts, which are also typed. And so type information is preserved with the type chain. Everything about ordering is the same, except everything includes type information. Okay, more formally speaking, a program, either a transaction or a contract, is a series of declarations and statements. The blockchain itself is then a series of programs, which is a series of declarations and statements, and thus is itself a program. So the entire blockchain is a program, and obviously individual transactions and smart contracts are programs. And in order to blockcheck a blockchain, or to blockcheck either a program or the blockchain, it is the case that if all prefixes of a blockchain, if all prefixes of a blockchain blockcheck, then the entire blockchain blockchecks, and vice versa. So there's an if and only if condition. So this says take all prefixes. So take a prefix, blockcheck it. If it blockchecks, it can form a new blockchain. And in fact, that's exactly how you extend the type chain, is that you take a new program, and if it blockchecks, then it can become the new type chain. So this is how you add to the type chain. And then the idea is that if you blockcheck, that blockchecking the type chain gives you linearity, realizability, and liveness. And this is happening universally across the entire type chain. And so these properties, in fact, hold for all contracts. And in fact, they are sound. Yeah, so this is nice. You get these safety properties, which is nice. But of course, as I said before, these safety properties don't capture all of correctness for a smart contract. And so ideally, type chains are extensible. So in addition to the program that you ship to the blockchain, you can also ship along what we call a type chain extension, which is itself a a type system. And so what we call this type system, yes.
No, I just wanted to let you know, yes, running out of time. So just the session should finish in 3 minutes. So maybe leave some time for questions as well.
Yeah, absolutely. This is the last slide.
Yeah.
Thank you.
Okay. Sorry.
Yeah, no, yeah, good. Thank you. So in addition to shipping the actual program to the blockchain, a program can include what we call a strengthened type system. A strengthened type system, so we say that a type system, here gamma prime, turnstile prime, e type checking to tau, strengthens some existing type system if and only if that type system effectively monotonically type checks fewer programs. All right, so this thing on the left is a strengthened type system. It strengthens the original type system, and it does so if and only if it admits monotonically fewer programs. So when you deploy a contract, the idea is that if you deploy a contract to the type chain, you can ship along with it a definition of a type system. Somehow the type chain checks that this is in fact a strengthening, and then it applies the miners, during block checking, applies the new logic of the type system, of the strengthened type system, to that contract and all contracts that depend on that contract. You don't apply it to the entire type chain, you apply it to that contract and any contract that depends on that contract. One example, just to sort of drive the point home, is that you can use this mechanism to implement a universal singleton type. So say that you have a property singleton that applies to a type tau, and you want to know a single value of this type tau exists in the entire type chain. You on your smart contract and you the property singleton for that type. And then you deploy this strengthening, which is these two properties here. This is the entire strengthened type system. The property on the left says that if it's not a singleton, we'll just type check it as regular. Just the strengthened type system is this delta type system. If it doesn't implement the singleton property, just type check it as regular. Otherwise, if it does, then check the singleton property. And we do that through a flow-sensitive type judgment here that effectively keeps a set of all the times that it's seen the type when type checking as a value. And we would say that this delta type system strengthens the original type system. So you would ship some encoding of this type system along with your smart contract. And just by doing that, you can ensure that your type tau has a single value in the entire type chain. And you can see how this extends to other sort of functional correctness properties. Okay, so that's all I really want to say about type chains. And that's really all I want to say about blockchecking the type chain. Just to summarize here, we've got blockchains. They're great. We can run arbitrary programs that are Byzantine, fault-tolerant, checked, and run by a bunch of nodes. And the problem is, of course, that they're very, very buggy. So how do we fix them? We've identified a few safety properties that are necessary for any correct smart contract. And we've also said, well, it's unfortunate, but it is the case that in order to soundly enforce these properties, you cannot do so with the purely language-based mechanism. You have to, in fact, redesign the entire blockchain. And we propose one way to do so, which is via a type chain, which is a type-driven language-aware redesign of the blockchain, where block checking checks these safety properties via a type system. Thank you.
Thank you very much, Sergio. We have maybe time for one question. Anyone want to ask something? Please raise your hand.
So I have a quick question. Is reentrancy a problem that you're addressing as well?
Yeah, it is. I didn't have time to quite get to that, but it is a problem. A lot of the bugs that result due to reentrancy, or rather the things that you would care about, the things that you would classify as bugs, manifest themselves either through, or rather would be obviated by the safety that we talked about. For instance, if you look at the DAO attack would have been impossible if the blockchain had guaranteed linearity. In general, however, there are classes of bugs that might result in inconsistent state if you expected atomic execution of a single method, say for instance. And so it is something that the blockchain, or rather the type chain, should enforce. The open question is enforcing these three properties sufficient to preclude the bugs that you care about due to reentrancy?